Okay, hello everyone. We'll get started. I'm Tony Roskilly. I'm Professor of Energy Systems here at Durham University, and I lead the EPSRC Network Plus on hydrogen fuel transportation. This webinar is part of a series looking at different aspects of hydrogen research applied to the transport sector. This month, we're delighted to welcome two speakers. One from giving an industrial perspective and one from academia. Our second presentation, it's going to be given by Professor Rachael Rothman, who's Professor of Sustainable Chemical Engineering at Sheffield University. She was the Faculty Director of Women in Engineering and achieving Athena Swan Silver Award, and strives to make Sheffield the #1 place for women studying engineering. Her research lies in the development and analysis of sustainable processes and clean energy systems. Her presentation is on hydrogen production methodologies. Over to you, Rachel.
Thanks, Tony. Hopefully you can see the slides okay now. So I'm going to cover a few things today. As Tony said, I've done a lot of work in hydrogen production, but I thought it would also be useful to give you some of the background to the HiRES program, which is going on at the moment. So we'll talk a bit about HiRES first and what's involved and all the different aspects of hydrogen production, use and distribution that we're looking at. A little bit about the South Yorkshire Sustainability Centre and what we're looking at hydrogen within South Yorkshire from a regional approach. And then we'll look at some hydrogen production technologies and work we've done there as well. So starting with HiRES, I guess quite a few of you who are listening may have heard about HiRES. There's been, over the last year, two UKRI-funded coordinator projects going on. HiRES is the one looking at research challenges, so particularly the kind of technical challenges within hydrogen alternative liquid fuels. And then there's been the sister coordinator project, HiAct, which is looking at the whole energy system and hydrogen's place within the electricity and other energy systems within the UK. And HiRES, I'm one of the three co-Is, and it's led by Tim Mays down at Bath. And what we've done over the last year and a half now is work through a theory of change process to really identify what the key challenges are that are preventing larger scale deployment of hydrogen alternative liquid fuels, but from a fundamental perspective. So looking at the drivers, the barriers to get there, what that gives us for opportunities for research. And we had a whole series of online workshops and then regional roadshows, and hopefully some of you were able to attend some of those and feed into them. And what that led into was a series of outputs that really highlighted some of the key challenges around hydrogen and how we might move forward. So the infographic on the screen is one of the ones that was produced early on from the production angle. And there's so many different angles of hydrogen production that will be important. And people often get stuck in the argument of, oh, should it be blue? Should it be green? Should it be any of the other colors of the rainbow that you can call from hydrogen? And ultimately, in the first instance, we just need the hydrogen to prove that the use of technology works. But the ultimate goal obviously has to be to move towards green hydrogen, because that's how you reduce the carbon footprint. But in the short term, there won't be enough green hydrogen for that to happen, and 95% of our hydrogen today is all coming from steam methane and other fossil processes. So looking at how do we within the UK meet our 10 gigawatt challenge, where can we use renewable capacity that may be surplus to generate hydrogen? Is it electrolyzers? Is it other technologies? And within this, we've also looked at the nuclear angle. So can you use nuclear heat for hydrogen production, and how? And I'll come back to that in a bit. And also, can you use solar, or do you just need the renewable electrons and go through the electric route of hydrogen generation? But that threw up quite a lot of challenges, as you might imagine. So I've highlighted a few of the key ones that came up on the screen. Challenge one, it says alternative catalyst to iridium, but it means iridium and all of the other precious metals and that are used currently in electrolyzers. So depending on the electrolyzer system you're using for hydrogen production, you need to have your electrodes, your electric catalysts in there. There's not enough iridium in the world to do all of the hydrogen things that we're currently planning on doing as a global direction. And so there needs to be alternatives to those. And there's a bit of a balance there between the environmental footprint, the availability, and also the cost and the efficiency of the device. And what we've been striding towards for a long time with technology is how to make it more efficient. And that's led us to these wonderful materials. However, if they're not available, we can't use them. And there's going to be a trade-off between efficiency that can be achieved versus cost of the materials in the first place. And that going forward, we may have to accept a slightly lower efficiency, but that it's cheaper. And there's a balance there that really needs to be looked at. And I'll come back to this in a bit, but this is where taking a whole system approach becomes really important, not just looking at the electrolyzer itself, but how are we using it? What are the materials in it? What do we do with those materials at the end of life of the electrolyzer? Can they be recovered? And what happens to them then? Another area that was highlighted was with the anionic exchange membrane. So how can we get a step change there in performance? And the same with the solid oxide electrolyzers. The solid oxide electrolyzers are the electrolyzer technology, which has the potential for the highest efficiency based on thermodynamics. However, because they operate at 600 to 800 degrees, there are some significant materials challenges there that really still need to be overcome in order to get the lifetimes that are needed for commercial production in that way. Seawater electrolysis was another one that was highlighted. If we didn't have to desalinate water first before putting it into an electrolyzer, that would make the system overall more efficient, but there's a real challenge there for the hydrogen production technology and how it copes with the ions that are and the salts that are in the seawater. Bio-based routes. So where would a bio-based route to hydrogen make sense? What technology is needed? How would it be deployed? And of course, with any bio-based route, you also have the tension of, should you use that bio-based material for this purpose or for another purpose? So should you be using it for chemical production or for agriculture, for food in the first place? So there's a lot of work going on there connected with the bioenergy supergen as well. And then the final one on the list was the solar and nuclear hydrogen production. And whilst solar and nuclear are obviously very different, they're lumped together because they both effectively provide an option for high temperature hydrogen production through different routes of getting the high temperature in, but both can be used coupled with thermochemical cycles. And I'll come back to the thermochemical cycles in a bit. Looking at the storage and distribution, what's really clear with hydrogen is there needs to be a wide range of different storage options. So it might be large volumes of hydrogen stored in underground caverns. It may be smaller volumes that are stored on board moving vehicles, for example. And how do you do that storage most effectively? How do you get the hydrogen in to whatever the storage medium is? And also equally importantly, but sometimes forgotten, how do you get the hydrogen back out again at the speed you need to get it back out? So it's not just the capacity in terms of storage of the material that's important, but also how fast you can get the hydrogen in and back out, depending on the job that it needs to be used for. And things that were really highlighted as challenge around there were cryogenic material behavior. And this is particularly relevant for the aviation industry, who are looking at, should they be moving towards hydrogen powered planes, for example, and that might need liquid hydrogen storage, which requires cooling, and then the materials and the metals that you're using to store it to be of a correct standard, meeting safety requirements for that. And there's a huge gap there that the aviation industry are very interested in. Developing permeation barriers. So this talks a bit to pipelines, and if you've got long pipelines, or equally if you're trying to store hydrogen for a long period of time, how do you ensure that all, if not most, of your hydrogen gets to where you want it to go without escaping through permeating through the material that's supposed to be holding it in place? Not just from a barrier development point of view, but also from a permeation and leakage and the safety associated with that. So if we start losing hydrogen along through the storage, then what happens to that? How does it disperse? Is it a problem or is it not a problem? Thermal energy recovery, that's from compression and liquefaction. So from an engineering perspective, how can you make that more efficient? And also the scale up of solid state storage. So a lot of the research being done on solid state storage at the minute is on milligrams or grams of material, and certainly not on the scale that we might need it if we're going to be storing appreciable amounts of hydrogen. And then from a cross-cutting perspective, sensor development, low cost and inline real-time sensors for hydrogen, and also the leakage and the failure. And this doesn't just apply for on Earth storage, but if you're going to have hydrogen on aeroplanes, any leakage or permeation out from your storage will be at high altitude. And hydrogen is in itself a greenhouse gas, and if released at high altitude has more impact than if it was released at ground level. And there's lots of work going on looking at how we try to quantify that impact of release at high altitude versus at ground level. Alternative liquid fuels. So alternative liquid fuels predominantly concentrates on ammonia, but could include other things like methanol as well. And it's looking at, well, how else might we store hydrogen in a way that doesn't end up releasing more carbon dioxide? And there's a lot of questions there around the reactivity, as well as around the separations that might be needed, and about the best way to develop the chemicals in the first place, and then how you get the hydrogen out, or do you use it as ammonia directly, for example? So some of the questions that came up were around the catalysts for ammonia cracking, materials for ammonia fuel cells, the safety around ammonia. If you're going to start using ammonia in more places than we do currently, then what are the safety implications, and what modeling is needed to understand those? If you combust ammonia, you can produce NOx, because obviously ammonia has nitrogen in it. So how do you reduce those NOx emissions? And this is also connected to burning hydrogen at high temperature. If you're burning the hydrogen in air, then you also have issues with NOx production. And so there's lots of work going on looking at burner design and how you can use secondary feeds in order to reduce the NOx production. Electrochemical synthesis of green ammonia. So how do we produce that green ammonia in the first place without having to go through the Haber-Bosch route, and the catalysts that might be needed to do that. And then the final one we've got is the end use. So we split it up into these 4 sections: the production, the storage, distribution, the alternative fuels, and the end use. And this is about, well, how might we use that hydrogen? So are we burning it in an internal combustion engine? Are we using a fuel cell? Are we using it as a reactant for a different kind of chemical reaction? And there's lots of different challenges and analysis that needs to be done in order to understand where we should be using it and what standards are needed. So can you use it in the iron and steel industry? And there is green steel being produced now using hydrogen, but not on a large scale yet. Redesign of cement kilns is an interesting one. Cement kilns and also brickworks, they burn an awful lot of natural gas, but if you switch to hydrogen, then the burning characteristics and the temperatures are different, and there's some real materials challenges that need to be overcome to drive that forwards. Burner improvements, I mentioned this one already. How do we reduce NOx production? And then development of electrodes and electrolytes for fuel cells, which share many of the characteristics with electrolyzers, but obviously now we're using the hydrogen rather than generating it. And a couple more cross-cutting things that came up was, how do we ensure that we have the hydrogen at the purity that the end use requires it to be? Because there's no point in making very pure hydrogen if your end use doesn't need very pure hydrogen, but equally it needs to be pure enough for whatever the purpose is. And it's not just how pure it is, but what are the impurities that may be there. So for example, if you have any sulfur components, then that will really destroy the electrodes in a fuel cell. And there's other challenges with different end uses. So this all fed into the vision for a hub to lead on from the coordinator project. And so now it's not just identifying what the challenges are, but actually doing the research to try and solve those challenges. And what was key when we were designing the hub is that we have technical themes and then cross-cutting themes. And as we've said, there's lots of technical challenges that we could look at within the hydrogen alternative liquid fuel space. But what's important is that the things we're doing are useful as well as interesting. So not just that there is a technical challenge, but if we solve it, it will help drive us in the right direction. So all of the research that is planned to happen within technical themes will be looked at through the lenses of the economics, the environment, the social, and the safety. And I lead the environmental theme there. And we'll be doing some work looking at those greenhouse gas impacts that we mentioned, but also looking at, well, which hydrogen should we use? How do we generate it? Where do we need to use it? What makes the most sense? Because ultimately the goal of producing hydrogen to use it is to reduce our carbon emissions. And there's lots of cases at the minute where we talk about maybe using hydrogen, where if you look at the whole system, you find out that the carbon actually increases rather than decreases. So how can we design the system such that we are moving to a low carbon situation? And one of the examples, I've mentioned it a couple of times, looking at the aerospace. So if you're looking at solid state storage within aerospace, there's questions there not only about the storage technology and how can you get the storage of hydrogen at the sufficient density and in order to get the hydrogen out, but there's also some huge safety questions there. This is a new way of using hydrogen. There will be needed to be new regulation. We need to look at the release at high altitude, or the potential release at high altitude, the economics of doing this, but also the social acceptance. And I haven't really mentioned the social side of things yet, but this is hugely important for the hydrogen moving forward. And there's quite a few studies, and you may have seen them, that if you go door to door and ask people what do they think about hydrogen, the two things that they answer is the hydrogen bomb and Hindenburg. And if that's the two things in people's minds, they're not going to want to get on a plane that's powered by hydrogen. So there's a lot of work there needed about social perception and also acceptance of hydrogen and how we might do that going forward. And it's not just the aviation industry. There's also lots of work going on from the social side, looking at, well, are we going to have more vehicles transporting hydrogen around the country, and what do people think of that, and how do we get them to accept that that might be the reality going forward? So one of the things we're doing is looking at some case studies, and South Yorkshire is one of the case studies we're looking at. Now, one of the reasons for this is that, and I'll ping on to the next section actually, because this connects a lot in with the South Yorkshire Sustainability Centre. And this is interesting because there are industrial clusters around the country, most of which are coastal. And there's lots of discussion about whether you can link hydrogen with carbon capture and storage, or carbon capture and utilization, and whether you can have hydrogen pipelines. But South Yorkshire is right in the middle of the country. There's no option for coastal pipelines, and any hydrogen that comes from the coast will be used by those coastal industrial clusters. So the industrial clusters of the steelworks, brickworks and glassworks in South Yorkshire need to find a different way to decarbonise than what some of the other large industrial clusters might be doing. So this sits within the industrial decarbonisation theme, which you see on the bottom left of this diagram. And the centre is set up so that there's three separate themes. We're looking at residential and transport decarbonisation. At the moment, that doesn't have a focus on hydrogen, but hydrogen is on their radar, partly from a transport perspective. So would it be public transport through buses, and how can hydrogen play a role there? And for anyone who's been to Sheffield, you know it's quite hilly, and that puts some constraints on how you power buses and how you need to refuel them and how often, etc. The agri-food decarbonisation looks a lot at carbon sequestration in soil, but there is a little bit of hydrogen connection there, but predominantly the hydrogen within this is looking at the industrial decarbonisation, because we have lots of large industry trying to work out what should we do and how do we do it. And the brickworks is a good example, because they have large kilns that are currently powered by natural gas, and they're thinking about, well, within the next couple of years, they're going to need to replace the current kiln. It's coming to the end of its life. This is a multi-million-pound investment for them. Should they replace like for like? But in that case, they're still going to be burning a lot of natural gas. Should they switch to a hydrogen-powered kiln? But actually, if they wanted to buy one, they wouldn't be able to do that right now. And the supply chain for kilns for brick manufacture, there are companies in the UK who make them, but right now most of the kilns they produce are being shipped overseas, and because they're not getting demand for low carbon kilns, then the kilns they're designing are still being made to use natural gas. And so there's questions around the burners, about the quality of the refractory materials, about the way the bricks will dry in a different environment. There's also questions around how would they make their hydrogen in the first place. So this picture is of South Yorkshire, a map of South Yorkshire, and the blue circles show you areas of potential hydrogen demand. So there's a cluster in the middle around Rotherham area. Let me get my pointer for you. Around here in the middle, this is where you've got some steelworks. You've got a cluster up here where you've got the brickworks. And this is the large emitters that have big impacts on the carbon emissions of the region, who are thinking about using hydrogen because they can't very easily electrify their technology. So they're looking at, well, what else can they do? And then if we put on here, what we've superimposed now is where we might be able to make hydrogen. And you can see the two circles are the areas I was just talking about. So potential sites of hydrogen production map quite well with large areas that may need hydrogen. But if we were to switch these to hydrogen and therefore produce hydrogen in situ or near. So if you had clusters producing hydrogen to then use it on an industrial scale, you would overpower almost all of your substations in South Yorkshire. In fact, even if you don't think about industrial decarbonisation, hydrogen production, if you follow the trajectory expected for electric vehicles, you already overpower more than 50% of your substations in South Yorkshire. So there's huge changes that are going to be needed on the entire electricity grid in order for us to move towards this hydrogen for industrial decarbonisation going forwards. All right, moving on to the next topic. This is my final bit. So thinking about thermochemical cycles and how other ways we could make hydrogen that isn't through electrolyzers. So for anyone that doesn't know, a thermochemical cycle is a way of joining different chemical reactions together. The ultimate result is that you split water to form hydrogen and oxygen. So the diagram on the left is the sulfur iodine cycle. You'll see water coming in and hydrogen's produced and oxygen's produced, and all of the other chemicals go round and round within the system. And the reason for doing this is you could spontaneously split water into hydrogen and oxygen if you took it to 4,000 degrees. But we're not going to do that. That's why we use a lot of electrolyzers through the electricity. But an alternative is to, instead of using one reaction, to use 2, 3, or 4 reactions, and that brings down the maximum temperature that's needed in any of them. So this reaction in the middle, where you add water in with sulfur dioxide and iodine, this is the Bunsen reaction. It occurs at about 120 degrees. And it will produce 2 acids, sulfuric acid and hydroiodic acid. And if you separate those 2 acids, your sulfuric acid goes up, your hydroiodic acid goes down. You then decompose them. And in that decomposition process, you release oxygen from one and you release hydrogen from the other. And then you recycle the iodine and the sulfur dioxide. Now, it all sounds wonderful in theory, and the reactions themselves are not the tricky bit here. The tricky bit is the separations. And in order to get those 2 acids you produce in the Bunsen reaction to spontaneously separate into 2 phases, you operate with a large excess of iodine and a large excess of water. And those 2 excesses drive the reaction forward, and then they ensure the separation of the 2 acids. But that then means when you try and decompose your hydroiodic acid that you're dealing with a lot of water and a lot of iodine, as well as the HI, which you're trying to break down. And that dramatically increases the energy burden on the cycle. Now you'll see there are a couple of red arrows for heat going in, and the sulfuric acid decomposition is the high temperature one. You need 800 degrees in order to decompose that sulfuric acid. And that brings with it some materials challenges, because you can't just build a metal or a glass reactor if you're operating at those temperatures. So you have to start thinking about specialized materials that are resistant to concentrated sulfuric acid at high temperature. And there's been quite a few research projects around the world looking at this. The reason these are interesting, both these cycles, I'll explain the other one in a second, is because they have potential efficiencies of greater than 50%, which is a really big achievement for both of them if we can actually get there. And in both cases, you're looking at high temperature heat input that could come either from nuclear or from solar reactors. So on the right, then you've got the hybrid sulfur cycle, and the box down the bottom left here, the sulfuric acid decomposition, that's exactly the same as the sulfuric acid decomposition you have in the sulfur iodine cycle. But in this case, the reason it's called hybrid is because you also have an electrolyzer step. So you have an electrolysis, not of water on its own, but of SO2, depolarized electrolyzer. And having the SO2 there means that the voltage needed is less than 20% than if you try to do just water on its own. So it dramatically improves the efficiency of the electrolyzer, but you also have to do the sulfuric acid decomposition step as well. And then you have to recover the oxygen and the hydrogen from the system. So there's been quite a few EU projects. This is the results from the high cycles one I've put on the screen. There's also been a lot of work going on in Japan, because if you're going to couple to 800 degrees, you're looking at a generation 4 nuclear reactor, so a pebble bed or an HTGR or something like that. And the Japanese have been, and the Chinese have been developing those technologies. And they've been looking at how you can improve that Bunsen reaction in the middle, the one where you need the large excesses. Because if you could reduce the excesses, it makes the whole cycle much easier to do. And they're looking at an electrodialysis process to try and reduce the excesses. Within the high cycles project, you can see on the left there, you've got a solar decomposition. This is a solar reactor to decompose sulfuric acid. That particular one's for solar, but the design is not dissimilar actually when you look for a nuclear heat to do the decomposition as well. What's key is that they're using siliconized silicon carbide to build the reactors from, because that is resistant to the sulfuric acid at the temperatures needed. And that picture in the middle is the largest heat exchanger at its time that was ever built from silicon carbide, because you need that kind of material and infrastructure in order to deliver the process on a large scale. The picture in the middle at the bottom is looking at some of the thermodynamics, because the sulfur dioxide, oxygen, water system is more complex than it might sound, in that you end up with two liquid phases and a vapor phase, and it makes it very difficult to model, because the thermodynamic packages that you may normally use don't have the detail that's needed of that multi-component system. So we're NNL in the UK are looking at thermochemical cycles now from a nuclear perspective and thinking about how might we use these going forward. The alternative is that you just take the electricity from a nuclear reactor and you directly power an electrolyzer, for example, without using the heat. But there are advantages to using the heat as heat rather than trying to use it to turn it to electricity first. And the final thing we've looked at, and this is coupling carbon dioxide utilization with hydrogen production. So this is a diagram of a solid oxide electrolyzer running co-electrolysis. So not just feeding steam into it to make hydrogen, but also feeding carbon dioxide in as well. And what that does is improve the efficiency of the carbon dioxide reduction. And what you make is syngas, CO and hydrogen. And once you've made syngas, you can make almost any chemical product or synthetic fuel that you would like with it. And this requires the electricity. Now, because you've got conflicting reactions, you've got electrolysis of CO2, electrolysis of steam, and you've got the reverse water gas shift reaction, which is a reversible reaction. That's the one here. And you can see, as I've written it there, going forward, you use CO2, and going backwards, you use water. So there's a complex interplay between those three reactions. And so what we did was some analysis of how do we actually understand what's going on in order to optimize that system. And that includes the thermal imaging to look at, well, what's the temperature profile across a solid oxide cell? That's just looking at a button cell. It's kind of a 10p piece size. Some Raman spectroscopy to look at the phases of the materials and how they change over time. And on the right, you can see the infrared, the drifts. It's infrared spectroscopy to look at, well, what are we producing? And what it actually showed is you produce a kind of temporary carbonate intermediate on the surface, which is what's then reacting. So that started to elucidate some of those reaction mechanisms that are important. Right, I'm going to stop there. I've covered quite a lot of different things, but I've put on the screen various websites and contact details depending on if you're interested in any of those, so you can look up more at what they're about.
Okay, thank you very much, Rachel. Again, a very interesting presentation.